Hey everyone, great to have all of you join us once again for Metaflow office hours this week. We have a very special presenter today. We have Saurabh Garg from Outer Bounds, who will be presenting today about his work of running, multi-cloud or rather, sorry, multi-account, large-scale workflows using Metaflow. Saurabh has been working here at Outer Bounds for a few months now. And prior to Outer Bounds, he was working at Databricks for 4 years, or about 4 years. And then prior to that, at Atlassian. So if you guys have, special things to say about Jira and Confluence, Saurabh might be the person to talk to or ask about all the things that go into building Jira. He has a master's in computer science degree from University of Pennsylvania. And Saurabh, it's great to have you here. Thank you so much for doing this. Over to you.
Awesome. Thank you, Shri. Thank you for the introduction. Hello, everyone. As Shri mentioned, my name is Saurabh, and today I'm here to talk about multi-cluster flows using Metaflow at scale. So the sort of setting out the agenda for the talk, we can talk a little about me. I want to introduce the problem statement, more importantly, the fine print with the problem statement, and then, how Metaflow, we use Metaflow to get around the particular problem at hand, and what some line items in a future work setting might involve. At any point in time, if there are questions, feel free to stop me, and we can talk about that. So about me, as Sri mentioned, I'm an engineer here at Outer Bounds, building an ML Ops platform that is powered by Metaflow. And here I am today I'm here to talk about how Metaflows helped us solve one of the most important problems, the dollar problem. So let's sort of dive in already. The dollar problem in my head is sort of something which relates to cloud spend. Pretty much a lot of folks who have migrated from the on-premise data center model over to the cloud are very cost conscious. They want to make sure that they are spending their dollars on cloud resources in the most effective manner and in a manner that gives them the most bang for their buck. Who wouldn't want to do that? So from the perspective of Metaflow, that we have customers, there are folks who have adopted Metaflow where they're like, oh hey, I ran only 5 flows, but my cloud bill, reached the $3 sign. What is going on? And any vendor who looks at that will just say, let me Google that for you. But no one really says that ever. I hope no one says that ever. So the actual problem at hand is customers run Metaflow flows on cloud instances, but the properties of these flows can vary widely, and they can have different runtimes. They can have different width, and I'll get into a little about what I mean by width. They can have different resource requirements. You can say, hey, I want CPUs, GPUs, disk, maybe at someday TPUs, and each of these flows you can imagine they are generating terabytes of metadata. Maybe the monitoring team at the enterprise is looking at is extracting out the CPU usage or the memory usage of those flows when they are running in memory on cloud instances. But the customers want to know the utilization of these expensive resources, right? Like someone got like 100 H100 GPUs, and they want to make sure that they've invested a whole bunch of money, and those expensive resources are at least being utilized, 35% of the time. They're not just sitting idle, just spinning their wheels, so to say. And once customers, once adopters of Metaflow have, know about the utilization of these resources, then they can go back and say, oh, by the way, these flows that have been running on these expensive resources, I want to adjust how many resources I'm asking for, or tune my usage of these resources so that I am, I don't end up in a situation where I am hogging up all the resources, or I'm asking for very little resources, or anything in between. And customers also want to understand what their historical spend is. Like they would like to say, hey, I have had these resources sitting in my account for the past, let's say, 6 months. How much am I spending daily? Like what is that dollar amount? So once you sort of distill this, in order to, like, if you were to distill this down into a single statement, the problem is we want to expose cost insights per Metaflow step to customers starting from an arbitrary date, let's say August 1st, 2023. So, but what is the fine print here? You want to access and query metadata across cloud boundaries, right? Account boundaries, because you can imagine a customer can have n cloud accounts depending on how they want to create silos within their company, or you can have hundreds of customers, each with their own cloud account boundary, in order to secure their cloud business. And even if you were able to, let's say, you were able to get into that cloud account, querying through massive amounts of data is like, finding a needle in a haystack. Usage changes daily. Like it's entirely possible that when the data scientists get in during the week, they are running, let's say, hundreds of flows during the week, but over the weekend, usage just drops off a cliff. However, you do want to make sure that your bill is getting, or like your cost report is getting updated every as of timestamp or some as of date. You can think of it as being very similar to your electricity bill. Like if you log into your electricity provider, they would say, oh, by the way, your projected or your bill based on your consumption as of date is, let's say, $100, which is high anyhow. So separate conversation. I remember I said the property of flows can vary really wide, and one of those properties is how wide your workflow can go, because depending on how wide the number of for eaches you want in your Metaflow flow, orchestrators like Argo or Airflow can sort of enter into uncharted territory, given based on the topology that they're running in. Of course, when you're writing any code, you want to make it maintainable. So let's say you were writing code for the $$ problem. You do want to make sure that the flow itself doesn't get so humongous that you are unable to even maintain the code going forward. Or any new individual joining your team is like, duh, what is going on over here? Of course, you want intelligent failure handling. Network, compute, storage errors should not mean that your entire flow goes off a cliff. And you want to be able to manage flows independently for every customer. So, for example, if you had 100 customers today and 50 new join, you don't want a situation where a flow, if it failed for a single customer, then it fails for every other customer as well. You want to make sure that there is a certain isolation between flows that are running for every customer in a system.
So, Saurabh, so in a way, this is kind of like, Metaflow for Metaflows, right? You're writing one flow that will do the, metadata reading, processing for cost management. And
right.
With the data that it is processing is basically data about other flows that others have already run.
Absolutely.
So when the users run, or when kind of sort of someone runs a data science flow, let's say, and the metadata for that flow has been captured, and now you're running a Metaflow flow, which is actually taking this metadata, or the goal is to take this metadata, crunch the numbers so that we can say how much, whatever this flow cost, what is the cost of this particular flow within the flow, what is the cost for this particular step, and so on and so forth. So Metaflow for Metaflows, right? Okay.
Absolutely. Cool. That's a
Very
really good way to think about it. Yes, exactly. So sort of, let's sort of throw out a big picture over here, right? So assume that, each of these big boxes, actually, can you see my mouse hovering over this by any chance?
Yes.
Okay,
yes,
sweet.
yes.
So assume that you represent a customer who is running Metaflow flows as one of these big boxes, and I've just called it AWS account one, and assume that there can be n customers who are running Metaflow flows, each within the boundary of their own AWS account. Now, as Sri mentioned, the problem at hand is for you to run a Metaflow flow that can then go out across these account boundaries and fetch down metadata about these Metaflow flows, crunch the numbers, and return return a report that is useful for customers to gain insight into costs, as well as how would you tune your flows in order to reduce your costs or increase your resource usage, and so on and so forth. So while we are on this big picture, I do want to highlight some of the basic Metaflow constructs that we used in order to solve this particular problem of cost reporting. So as you can see, we use the add branch operator, the add retries, the add schedule, the add project. There were trigger on finishes. We use conda base in order to create repeatable environments for execution of our own flows. But let's sort of start right at the top. So what this is actually telling us is the cost reporting flows themselves were decomposed into 3 flows that were daisy chained together using the trigger on finish decorator. Essentially, what that means is when the cost report data accumulator flow runs and completes, it will basically trigger the cost report query data, and so on. It will once the cost report query data finishes, it will trigger the cost report generation flow. This daisy chaining of flows was basically they were basically connected together via 2 very important things. The first being the act project decorator, which basically allowed us a mechanism to manage these flows at scale. And what I mean by that is when you have n customers, then you can use if you have the project decorator, then it allows you to create separate branches, and with those separate branches you can configure the execution of these flows for each of these big AWS account boxes that I have drawn up north. Now, I remember I spoke about in the fine print that when you're reaching out across these network boundaries, then you do want, the first question is how do you even access the metadata that might be stored in one of these AWS accounts? Because by default, no one has access. So we relied on something called IAM role assumption that AWS exposes as a mechanism to access data that might be sitting in, let's say, some S3 bucket in some AWS account. So we basically worked with our customers to create these IAM roles that had very, very narrow permissions to access metadata that they might be spitting out and storing in one of their data sources, which served in one of the S3 buckets, which served as a data source for us. But the thing with the data source is the data itself in a bucket is sort of not in a very structured format. So querying through that data is sort of quite complicated, which is where we sort of used a couple of AWS constructs again called Glue and Athena. So Glue is basically the service in AWS that allows you to create views on top of data that might be, let's say, coming in from an S3 bucket. And Athena allows you to run queries over those Glue tables. However, if you notice, there is a whole bunch of arrows that is sort of going across network boundaries. And network, as we all know, is a very finicky place to be, with a lot of random failures that you can run into. For example, you can run into you suddenly lose an HTTPS connection because the remote socket closes the connection, or you get kicked back from AWS services because, let's say, you breach certain rate limit thresholds, or one of a million different things happens. So that is where the retry decorator in Metaflow came to our rescue, where we can basically say that we can filter out a whole lot of whole lot of failures that are retriable, and we don't have to really fail the entire execution pipeline just because we ran into some rate limiting error, which is recoverable from the AWS side as well. Another important thing to note here is I mentioned that we decomposed our flows into different we decomposed the pipeline into separate flows. But where are these flows running? Because remember, I also said costs change every day, because hey, my data scientist today ran a new training flow on their on some H100 GPUs, and they want to know that what the next day they want to know, hey, how much should I spend on that? So you want to be able to make sure that you are running your flows at a cadence. That is where we use the at schedule decorator. So we said, hey, I want to be able to expose cost reports for the past day using the at schedule reporter, but using the at schedule decorator with the idea that with the idea that we remember I said we have an as of date, so the at schedule decorator will run once the as of date has passed the midnight boundary, and then it will kick off this pipeline, which runs as an Argo workflow. So now that we've sort of seen the big picture, we'll keep coming back to this, but I do want to take a second here to make sure there are no outstanding questions, either if someone has questions or questions in the chat. Okay, I don't see any questions here.
Yeah, there are no questions in the chat. I have one question. So, so basically, each of those accounts, the AWS account 1, AWS account 2, account 3, and so on up to account N, there are people who ran flows in those AWS accounts. The metadata for those runs, whatever, eventually was stored in an S3 bucket in each of those accounts. And then from the processing account, which is kind of sort of at the bottom, we are going to run a Metaflow flow or multiple Metaflow flows that will reach out into these accounts and kind of sort of read the data and process the data. So each of those colored arrows basically, will that be a for each? Where, let's say, if you have n accounts, there'll be n for eaches. In each instance of that step, like you mentioned, we'll assume a role for that particular account, read the data, whatever, process the data, and then so on, whatever, save some results.
Exactly, right. Okay. So you can imagine the problem sort of spiraling as the number n becomes really, really large. If you have, let's say, 100 accounts, or if you have 500 accounts, then the value of n is always progressively increasing, which is why the for eaches that you're running then suddenly start becoming really, really large, which also is a reason why you want to decompose your flows. Because an alternative, if you think about an alternative world where we did not use the add branch decorator, you would still have all of these accounts that are running on a single branch. And then on a single branch, you sort of start having many accounts, and the width of the cost reporting flow just keeps on increasing. But when you start then using add branch operators, the add branch decorator, you can then say, oh, on this branch, I will run the flow only for a single customer. So then, yes, the trade-off you're making is you now have n branches, but each branch still has just the one sort of customer that you're processing the data for. So that is the trade-off that you're making. And we'll sort of get into the for eaches in a little while as well. That is a really, really good point about when you think about decomposing flows, should I sort of have a single flow across many accounts, or should I have n flows? Should I have n branches with one account on each branch? So that is something to sort of think about. in our case, n is a very, very large number, could be a very, very large number. So it made sense for us to break it down with add branch decorators and also other reasons why we want to do that. All right. In case there are no questions, let's sort of keep this party going. Sorry. All right. So the first step, let's sort of look at, let's sort of dive a little deeper into what are each of these flows doing individually, and what were some of the challenges from a scale perspective that we ran into. So from the first flow of the data collection step, as Shri also mentioned, was a step where a single flow had to reach out across network boundaries or across AWS account boundaries in order to collect metadata that was stored in an S3 bucket in a customer's account. This is raw anonymized data, which is sort of indexed daily. And we had to create IAM roles across every AWS account to access only that S3 bucket, essentially operating from the perspective of least privilege. And then we had to map this raw data into structured glue tables so that flows that were down the line, like the cost report query data flow, could then run queries on this view of the data that had been created from the S3 bucket itself. The data accumulator is also the first step in the Metaflow flows. As I mentioned, these flows are all orchestrated via Argo. Metaflow, I believe, also supports orchestration via batch as well as step functions. But Argo, for our purposes, was a nicer alternative, given Metaflow sort of supports the @schedule operator with Argo, as well as we have more infra setup for running Argo workflows on our end as well, rather than step functions or batch or Airflow or whatnot. Even though I think Metaflow has, you can use Metaflow with Airflow as well. So as I said, @schedule was because we had to the nature of the problem where costs change every day and you want to expose newer reports at cadence. @schedule was a great fit for this particular problem, and running it via Argo was much more easier for us. And depending, the one thing that you always want with any code that sort of executes in production is repeatability, because code repeatability of the environment, because code has been running in production for 3 months and suddenly one day it doesn't run because, hey, someone did not pin down a dependency and the dependency just got updated and all sorts of chaos ensues, which is where we sort of went down with pinning down our dependencies using the @conda-base operator decorator, just to make sure that we have environments that can have repeatable runs. And as I mentioned, we use the triggers on finish in order to daisy chain up these flows, so we can so Argo events that trigger when a flow completes can trigger off the flows downstream. The data query flow, however, sort of has some interesting quirks that we should talk about, though. So the first, as I mentioned, the data query was happening from Athena over the views in the glue table, views, aka the glue tables. Now, these intermediate results of Athena, so once Athena executed the query and created some intermediate results, they were repatriated to local environment for processing in the next flow, and we sort of look into that in a second. But there were some scale issues that we ran into when we sort of ran this particular flow. So let's sort of get into it. The first issue that we ran into was disk pressure. So imagine you have a data scientist team that is running 3,000 flows, and each flow is sort of creating gigabytes of metadata over the last 24 hours. Now, when you're querying out all this data and you're repatriating it to local environment and you're doing it across n accounts, the problem you run into is there is a lot of this pressure that sort of gets created, because each pod in each Metaflow pod only ever gets so much amount of disk by default, which is about 10 GB. Yes, we realized later on that we could up the amount of disk that we are giving our pod, but it was only after we ran into the issue. So when you're sort of declaring your when you're declaring your steps, when you're pulling down, let's say, large flat files to local environment, make sure in the at resources decorator you provide disk, and then you can say, hey, I want 100 gigs, or 500 gigs or a terabyte or whatnot. The next issue we sort of ran into was parallel queries. So if you can imagine, we are in a situation where a single processing account is reaching out across n accounts and kicking off n Athena queries all at the same time. And AWS sort of has this higher rate limit, which basically says a single account, if you're trying to access, if you're trying to hit AWS services across n accounts, you are limited to a certain number of requests that will go through at a time, which is sort of the limit that we breached. However, so one of the Metaflow features that we used in order to control this was to use the max workers knob. So let's say n was 500, and the max number of queries you can make against AWS Athena is, let's say, 100 a second, right? So in order to make sure that we would not breach that rate limit, we set the max workers knob, let's say, to 50. And you know that even if you want to make 500 queries, then only 50 pods will come up at a single time, and each pod is only ever making one query, so you are never ever going to breach that particular rate limit threshold against AWS. Excuse me. And the last bit was cost. When I sort of introduced the problem, I said that we wanted to make sure that we were exposing cost reports from cost reports not only from the day we released the feature, but also we wanted to go back in time and expose to customers, hey, yes, the feature is starting to roll out today, which might be, let's say, the 15th of December, but we've backfilled data for you starting all the way from August 1st, 2023. So it's not like you're going to end up on an empty screen. And in order to sort of backfill all that data, we ran into the parallel queries. But in order to also backfill the data, there was a lot of dollars that we were spending per terabyte of data that was scanned via Athena. Now think about it. If you have flows that are sort of generating the order of gigabytes of metadata, and you are scanning through data over 90 days, that quickly adds up the cost in the cost reporting flow itself, right? So in order to make sure that we were not repeatedly running the same queries over and over again, we utilized a sort of caching mechanism for those queries that had already been executed, and we reused them in subsequent queries. So making sure that the dollars that we are spending went a long way, rather than just repeatedly spending those same dollars over and over again. The last step in the puzzle, which is the report generation, now we sort of come to the last step. So just to recap, we've sort of, until now, we have gone ahead, we've created the virtual view in glue tables. We have, we mapped the raw anonymized data from the data source into a view, which was the glue table. We then ran Athena queries on this glue table, and we repatriated the data back to local environment for processing. And now we are at the last flow in our daisy chain flows, which is the cost report generation. So let's sort of look at some of the issues that we ran into at scale when you're running this particular flow. The first issue we ran into was, remember, we were doing backfills for over 90 days and for n accounts. So for each account, we were doing a for each for n accounts, and for each account we were doing backfill. We were doing a for each over 90 days, which means that we were effectively doing n into 90 wide for each. The first issue we ran into there was, when you do this wide of for each, you remember in Metaflow, every for each has to be completed via a join step, where you say, oh, I've completed all these for eaches, now I need to join before I can go forward in the DAG. When that join step sort of started to kick in, one of the things that that Argo sort of does is, in the Argo workflow template, it has a field called the pod status. And in the pod status, it was basically storing the task pod identifiers for each and every pod that had contributed to the join itself. And at some point, it sort of exceeded, the workflow template itself exceeded the HCD 1 megabyte limit. Because of that, you can imagine the situation was, we had run a flow that had been running for, let's say, 2.5 hours. And then it, just before the last join had to complete, it exceeded the HCD 1 megabyte limit, causing the entire thing to fail. We reduce this redundant task pod identifier information in the task template by a factor of 3x. These pod identifiers were getting stored in 3 places. So we sort of brought it down to a single place, and then we added pointers to the fields where the pod identifiers were present, which is how we were able to increase the for eaches, the width of the for eaches as well. While running the report generation, we needed resources both on disk as well as memory, because we were loading up a lot of the intermediate query executions into memory for processing, which caused ooms on the Metaflow pods that were running to create the reports, the cost reports. Again, the at resources decorator came to the rescue, where we were able to say, hey, when you're running the pods for the report generation flow need a little more memory. And so we were able to get past that.
One quick note about the HCD limit of 1 megabyte for Argo. So there was one PR that was already, like Saurabh was saying, that was merged. So that reduced the number of times the names of those previous steps get put into the flow, and therefore, into the step, and therefore it reduced that substantially, but it still is not fully ready. There is a second fix that Argo suggests, that we use some database for offloading these things that we need to start supporting in the open source Metaflow implementation. So we'll need to look into this. Sorry, go ahead.
Right, exactly. So, after all of these flows, how's it looking when all of these things come together? So, for example, this is a screenshot from our proprietary out of bounds platform, but that used Metaflow in order to get to crunch all of these numbers and generate a report. For example, in this flow, you can see that a particular step ran for a couple of days and 17 hours, and it used a max of 8.8 CPUs, but I had requested only 2 CPUs, or it requested correspondingly, I requested, let's say, 8 gigs of memory, but I only ended up using 3 gigs of memory. So that sort of, as looking into this, I can immediately say, hey, I really need to up the minimum amount of CPUs that I'm giving my this particular step, and I'm asking for a lot of memory, so I can effectively reduce the memory on this particular step, and so on. Managing these flows, I've sort of been talking about this throughout the talk, about how we daisy chain the flows together using the project decorator. Now, The project decorator, so one of the things that we that was absolutely necessary for us to reduce the on-call burden of having all of these customers sort of running on a single flow, and then one customer sort of breaking everyone else, which is why we said, oh, we are going to break out the customers into their own separate branches and create that separation of concerns. For other folks, it might not be necessary, but highly recommend that when you're running stuff in production, you can create a separate production branch, and you can have a separate dev branch or a separate staging branch, so you can iterate more quickly. Basically, sticking to the nice things about software development, nice practices about software development already. We configured PagerDuty integration. Metaflow, when you create a Metaflow flow in Argo, it allows you to specify PagerDuty keys. So let's say a flow bombs in production, then we get an on-call individual will get paged that, hey, something has gone wrong, and then they can follow runbooks to figure out what really went bad. We use extensively the client APIs that Metaflow has to debug flow failures during the development of these flows. Let's say, the happened, or hey, I had assigned this variable to self. What is the value between steps? What got correctly threaded through after a huge for each, and so on and so forth. There is this really nice mechanism where, let's say, in my daisy chaining of flows, if the first two flows ran correctly, and I want to rerun the cost report generation flow, but for a different cost report query data, then you can run that. You can trigger the third flow, the cost report generation, using some earlier version of the cost report data flow, using the dash trigger option that Metaflow has, and you can just specify cost report data and give it the Argo run ID. So it is very flexible in that terms as well. Now, talking about future work from the perspective of cost reporting, we do want to predict cost reporting based on past usage. We do want to improve our data ingestion pipeline so that we are not really reaching out across all these network boundaries, and sort of improve querying costs across customers as well. Because right now, as I said, we are sort of passing through terabytes of data and then pulling down gigabytes, and then we are throwing a lot of resources at the problem. And the most important, as Sri mentioned, we want to increase the for each width even more by offloading Argo workflows to external storage, which would be a huge game changer for us. Hey, that's it. That's it, everyone. Happy to have a Q&A. Go back over any of the things that I presented. Talk more about Metaflow. But yeah, just wanted to thank everyone for taking the time and joining the office hours today. We can open the floor up to questions.
Yeah, very cool. Thank you, Saurabh. This is awesome. Any questions, David? Go ahead.
Yeah, I have a question. So with the cost of disk usage, like let's say the artifacts you have, how does that work with I guess the caching between different runs of a flow? So my understanding is if you save a variable in 3 flows and the variable equals just, let's say, the integer 1, it only gets saved once in S3. So how do you which flow do you assign that cost to, essentially, is what I'm asking.
So the caching piece that I was referencing was with respect to the results of the Athena queries that were running against Glue. So imagine Glue is basically there's a one-to-one map between a Glue view and what is stored in the data source over the past 24 hours, right? And this can be about terabytes of information, of metadata that has been collected. Now, when Athena plows through all of those terabytes of data, you're incurring costs, right? And that the resultant query can be of the order of gigabytes. Now, let's say you've run a query the 30th of January. Now you want to come back on the 7th of February and you want to say, hey, I want for some new cost reporting feature, I need to go back, let's say 30 days to figure out some additional metadata so I can punch it into my cost reporting crunching. Now you're not going to go back and sort of keep running these queries over and over again, right? So Athena allows you to basically store the output of the executions in an S3 bucket as well. So it was as simple as basically saying, hey, I've run an Athena query. Here's the output that I have. I'm going to dump it into some S3 bucket for later referencing if I need it, if I need that.
Yeah, but does that take into account like there's, I guess, no new costs? In what I'm thinking of is if you, let's say you run the simplest of flows, the hello world flow, where you save one variable hello world to self, and you run it 1,000,000 times. This would be like incur the much less cost than, let's say I do the same thing, except I now save a random number generator and I run that 1,000,000 times. I'm going to get 1,000,000 different artifacts on S3. Like,
So one small, I think, point
so I guess
to
like,
add.
okay, go ahead.
No, go ahead.
I was also kind of wondering, like, so one thing that we were kind of looking into is actually if you could use something like this to delete old flows without, like, safely delete a flow without deleting something that is still used by a new flow.
So one thing to note here is, I think for the most part here, the cost, I think it refers mostly to resource utilization, and kind of sort of the example that was given that I requested 2 CPUs, but I used 8. So there you're like actually overusing the resources that you're actually requesting. So you might as well request 8, so you're guaranteed to get it. The other way around, which is I requested 8 gigs of memory, but only used 2 gigs. I'm actually wasting some resources. If I use just the right amount, I might be able to bin pack. If I bin pack, then I'll reduce the number of nodes I'm running on. That will reduce cost. The cost of S3, especially about the artifacts that get stored, like there are 2 parts. One is the artifact produced by Metaflow itself. So if you have self.x equals 10, you're right that the 10 gets checkpointed when the step ends and it gets stored in S3, and the same x might get referred to in like 5 flows down the line. So the artifacts produced by Metaflow is one cost. The artifacts produced by Athena is a different cost. I mean, imagine Athena in this case is just some workload that is producing JSON files that are outside of Metaflow. So when the processing account pulls down a JSON file, today it is generating one JSON file. Tomorrow it will generate a different JSON file for tomorrow's needs and all that. So these are 2 different storage artifacts. And you're right that Metaflow storing artifacts and can it, leverage, consistent hashing and what are the content addressable storage that Metaflow has. How does that affect the cost of flows? If I understand this right, at this point, kind of sort of that is a little different outside of what is currently being done.
Okay. All right. And I guess another question would be, is there a reason you're just not using something like Prometheus on whatever you're running to collect this data? I mean, that's what we do generally. We just use Prometheus and check all the pods, and I have a label or even the annotation of the step name, and then you can calculate how much CPU usage and memory usage there was used and requested.
Yes. Great point. Great question. Well, the metrics metadata that we collect, yes, we can throw that into Prometheus and we can build really nice charts. However, when imagine this, you in an cloud account, there are resources like you can have different types of GPUs, right? You can have different types of EC2 instances. You can use You can use on-demand instances, spot instances. You can have a 1-year contract with them that you're paying upfront, and there's a different pricing. So while usage can easily be charted using the same metrics metadata via a Prometheus server and in Grafana, costs themselves need a little more finagling in order to make sure that you ran a flow from 1 a.m. to 2 a.m. UTC, and this is the cost that was associated with it, because we use certain resources. What type of resources did you use? For how long did the thing run? In order to figure all of that math out, Grafana is not really the right place for it. You want it's a higher level of insight that you're getting once the cost report generation flow has executed. But if you wanted to say, hey, I want to know all the flows that ran from a certain time to a certain time, absolutely go to Grafana. You can absolutely see that information. But it is unlikely that you might. It's possible, let's say you did not have the instance type tag on the metrics, or you did not know what step ran when that flow was executed. It's entirely possible you might not have those labels in Grafana because you might not because the cardinality of those tags can be really, really high, and the monitoring team might not want to store those tags because it'll create a different time series for each one of those executions.
Also, another kind of sort of thing to add to that is Prometheus especially has had issues that we've read about for long-term retention. So if you do store, we would love to hear how long do you store data in Prometheus, but if you start storing it for a really long time, like outside of more than in the order of months, then there are problems that can arise with respect to the query times and resources uses and so on. So we do use some not Prometheus, we use Victoria metrics, but they only store data for a finite amount of time. And then S3 is kind of sort of the best way to kind of sort of use long-term storage. So this data gets dumped from Victoria metrics into S3, and then with S3 you can query a lot better. You can do a lot more number crunching. You can do a lot more kind of sort of. There's just a lot more flexibility. There is lots of other data that goes into S3, by the way. It's not just these metrics. So this correlation between these numbers, these metrics, and other events maybe, or things like that kind of sort of can be very powerful. So that was one reason to store it. This thing, Prometheus can help for sure, and it might for data that is more recent and in the last few days or something like that. It should be possible to query Prometheus as well. But as I said, for long-term retention, it's probably not an option. I mean, there are. I know there is Thanos, but there are also lots of reports. We need to test this out maybe to see at what point does the long-term retention story for Prometheus hold true.
Yeah, I don't think we use it for that long, but then
Yeah,
we take some aggregate of the Prometheus
I
and
see.
throw it into a different database.
I see. Yeah, that seems reasonable.
Yeah, we could roll up. Yeah.
Cool. Any other questions, folks on the phone? Going once, going twice. All right. Well, once again, thank you, Saurabh. This was awesome. Very, very cool to see this kind of sort of, operations at scale and multiple accounts and everything. Very cool. So thank you so much for presenting today. And thank you so much, everyone else, for joining.
Yeah, thank you for having me. Thank you.
And awesome. And I'll see you guys on Feb 14th. I'll send announcements about the next session sooner as we approach the date.